Welcome to MrCScience.com's video on pressure, volume, and temperature of a gas. We're going to walk through definition of pressure. We're going to talk about Boyle's law and Charles' law, and we'll get to the final one, the combined gas law. So we're going to combine all those three. Let's talk about gases and pressure. So let's start with pressure. What is pressure? Well, pressure is a force. Whoops, grab the right tool. Pressure is a force applied over an area. Force over an area. That's not a very complete circle. Okay, so gases uh, apply pressure to objects they come in contact with. Why is this? Well, we remember that in solids, all the atoms or molecules are stacked right next to each other. Any movement they do is vibration. Liquids, same type of thing, but there's a little more freedom of movement, but still constrained by gravity. Gases have enough energy to break free of gravity's bonds somewhat. If they completely broke through, we wouldn't have an atmosphere on the planet, but they're much less constrained by gravity and they can move. And so gases aren't up against each other. Molecules and atoms of a gas aren't up against each other. So they're flying around. If they come in contact with a object, they'll bounce off that object, and that applies a force against that object, and that force over an area is pressure. Now we define force in newtons, so in our force equals newtons, often written as capital N. A newton is really a kilogram meter per second squared, but that's more of a physics term, don't worry about that. So if we got newtons over an area, we've got newtons per meter squared. An area is metrically meters squared. That equals a Pascal, PA. So 1 Pascal is 1 Newton meter per second squared. Pascals are a way that we denote pressure from gases. Another way we denote one is atmospheres, written as ATM. 1 atmosphere, our atmospheric pressure changes, but the variation is relatively small compared to the overall pressure. 1 atmosphere is considered 101.3 kilopascals. Remember, a kilo means 1,000, so 1,000 pascals, or basically 101,300 pascals is 1 atmosphere. That's a way that scientists measure atmosphere. A couple other ways they do it. They measure it in millimeters of mercury. If you have a column full of mercury, closed column, you've got your mercury in there, and say a pool. The pressure, the atmospheric pressure, pushes down on the mercury, causing the mercury to rise to a point where the pressure inside the tube equals the pressure outside of the tube, because in here you've got a gas as well. Mercury itself does not really compress well, so that works out well, so they measure it in millimeters of mercury. Last one is torr, measured in torrs. Torr is a very physics-related measurement. We're not even going to get into that. So pascals, atmospheres, millimeters of mercury, and torr are the 4 different ways they measure atmospheric pressure. Now, taking those atmospheric pressures in mind, or keeping those in mind, we're going to talk about Boyle's law. Whoops. Boyle's law. Boyle's law can be represented as pressure times volume is constant. So if you adjust the pressure, if you increase the pressure, the volume has to go down. If you increase the volume, the pressure has to go down, vice versa. This can be written in a different way. P1 V1 equals P2 V2. So If you vary one of these, so say we increase the pressure here, then the volume here has to go down to make it equal. So basically pressure and volume are, what's the word I'm looking for? Well, directly related. So as you increase one, the other has to decrease, vice versa. Pressure 1, volume 1 equals pressure 2, volume 2. Now, that's useful, but let's talk about the other two laws to really bring it all into play. Let's talk about Charle's law. Scroll down here. Oops. Sorry about that. Sorry, I saw a little web project I was working on there real quick. Okay, so Charle's law. Charle's law, like Boyle's law, relates to objects of gases, but this one is pressure. Still works with pressure, but if we put over temperature, that's constant. Saying that as we vary temperature, pressure will change. As we vary pressure, temperature will change. If we increase temperature, in order to stay constant, pressure is going to have to increase along with it to stay the same number. If we decrease pressure, temperature is going to have to decrease to stay constant. This can be written much like we did the Boyle's law. P1 over T1 equals P2 over T2. So again, if we increase pressure, in order for everything to remain the same, temperature is going to have to increase for them to be equal. So let's see. So again, relates pressure and temperature. Now, what's really works is what's called the combined gas law. Combined gas law combines Charle's and Boyle's laws. Combined gas law. So combined gas law is pressure times volume over temperature is constant. Now in, here just a second. In Boyle's law, in order to keep this constant, we kept temperature constant. So Boyle held temperature constant and just changed pressure or volume and see how the other one related. In Charle's law, he's got pressure and temperature. He held volume constant. So he kept the same volume and just based on varying temperature and pressure, he watched what happened and saw that they were constant. Well, in reality, the combined gas law puts them all together. Pressure times volume over temperature is constant. So now all three of them rely on each one. This again, whoops, can be rewritten like the other ones. P1 V1 over T1 equals P2 V2 over T2. So if you have your starting pressure, volume, and temperature, and you vary one of them, you can figure out the other two working out here. So, and you'll see if like Boyle, he held temperature constant. Well, we can take temperature out of the equation, and we got P1 V1 equals V2. If we are like Charle's law, and he held volume constant, we can take out the V's and say P1 over T1, P2 over V2. So hopefully that makes some sense to you. There is one thing you have to make sure you do on this though. Temperature has to be in degrees Kelvin. Why is that? First of all, refresher on degrees Kelvin. Kelvin goes from absolute zero, which is what, negative 273.15 degrees Celsius. That is 0 degrees Kelvin. And it goes up there following the Celsius scale. So anytime you want to convert to Celsius, just subtract 273.15 from your number to get your Kelvin scale. So that would mean 0 degrees Celsius is negative 200, or yeah, go the other way around. Just a second. Yeah, let's redo that. So basically this means Kelvin, Kelvin equals Celsius, degrees Celsius minus 273.15 degrees. So Kelvin is that. So in this, use Kelvin. Why do we use Kelvin? Well, if we use Celsius, Celsius goes up to, well, let's take water, 100 degrees Celsius. It boils at 100 degrees Celsius. What does it freeze at? It freezes at 0 degrees Celsius. Water can also get much colder than 0. But what happens if we put 0 in for one of our t's? What happens when you divide by 0? You get an undefined number. It causes issues. And what happens when you go negative? Then you get a negative number, which makes no sense whatsoever anyway. So nice thing about Kelvin, it's always positive and it never goes to 0, even though you say, hey, here's 0 degrees Kelvin right here. But in reality, scientists cannot get to 0 degrees Kelvin. If you tried to get to 0 degrees Kelvin temperature, the volume would have to drop to 0 as well, and pressure to 0. So, or one of those, volume or pressure, would have to drop to 0, and they haven't found that yet. So they've gotten extremely close. I mean, almost, but chances are they'll never actually be able to get to absolute 0 because of this. Just kind of an interesting caveat. So always use degrees Kelvin for your temperature. Pressure and volume doesn't necessarily matter as long as you use the same units on both sides of the equation. You can use pascals, atmospheres, torrs, millimeters of mercury, that's fine. Volume, you can use meters, centimeters, you can even use inches or feet, as long as you use both on the same side, because we're effectively setting up a ratio here. So yeah, see what works out best for you. In your book, you'll always probably use atmospheres, or you could use torrs as well, but you'll always use metric for volumes, so milliliters, liters, fun things like that. So if you have any questions on this, feel free to drop me a line at mrc@mrcscience.com. Thank you.